Yeah, you said it was interfering with your lunch.
Yes, indeed. Well,
thank you for sacrificing your lunch today.
No, I'm not sacrificing. I'm just delaying it.
We had a bigger breakfast today for Satya's sake. Okay. There are quite a few names I don't know, but I'm going to let them in because this doesn't get that wide a circulation. Okay. So we are at the hour, and I think we can get started. I know there are some more people who will join. So, Shoto, you want to share your
yeah,
screen?
let me share my screen now.
Okay. Oh, Chris has joined. Hi, Chris.
Can you see the slides?
Yes, very nicely. Okay, let me. So, I'm sorry we had to cancel one of the lectures. Hemachandra Subramaniam was going to give that lecture from Durgapur. But I had to cancel Hema's lecture because our mail system changed. And I had no control over sending out emails for a while. And Zoom, as a result, would not let me in. So sorry about that. Hema will give his lecture next month. So that's coming up. He's a young biophysicist. He was actually one of our former grads from Buffalo quite a few years ago, and one of my stellar students. And some of you know him quite well. All right, so today we have a really fantastic guest. Not that any other guests are less fantastic, but it is always difficult to catch Satya, and so it is a real delight to have him. Speaker is Professor Satya Majumdar from University of Paris-Saclay, CNRS. And Satya will speak on extreme value statistics, an overview and perspectives, an area in which he has done a lot of work and written some excellent reviews, as you may know. So Satya's brief bio, I'll just go through it because, and there's the least I can do here. And Satya, thank you really for taking your time on a Saturday afternoon.
It's a pleasure.
Instead of planning for the next nice meal, showing up here. So Satya Majumdar is a research director at CNRS in France, working at LPTMS, University Paris-Saclay in Orsay. He did his PhD in 1992 at the TIFR on self-organized criticality in sandpile and related models. Excuse me. After doing his postdoctoral work at Bell Labs and Yale University in USA, he joined TIFR faculty in 96. In 2000, he joined CNRS in France, first at Paul Sabatier at Toulouse, and since 2004 at Saclay. Besides this, he also holds several honorary positions as an adjunct professor, excuse me, at the Tata Institute in Bombay, Weizmann Institute in Israel, Raman Research Institute in Bangalore, and is also an associate at the Higgs Center at Edinburgh. He has made outstanding contributions in many different areas of statistical physics, stochastic processes, and random matrix theory, with applications ranging from granular systems all the way to computer science and biology. His work is characterized by a very elegant mathematical analysis of physical problems, leading to a plethora of beautiful analytical results. These have not only provided deep insights into the underlying physics, but have also advanced fundamental mathematical understanding. His work is probably almost as well known to probabilists and mathematical physicists as to statistical physicists. Some of his most important contributions are on self-organized criticality of sandpile models, on stress propagation in granular systems, on persistence and first passage properties in non-equilibrium systems, on sorting and search problems in computer science, and on extreme value statistics of random correlated variables. His seminal work in random matrix theory has applications for growth models, biological sequence matching, conductance distributions in quantum dots, entanglement entropy in pure random systems, and much more. He is a recipient of several national and international prizes, including the Paul Langevin Medal of the French Physical Society in 2005, Excellence Award by the Tata Institute Alumni Association in 2009, European Physical Society Prize for Statistical and Nonlinear Physics in 2019, CNRS Silver Medal in 2019, and the Gay-Lussac Humboldt Prize of the Humboldt Foundation in 2019. So with that, let's welcome Satya, and it's all yours.
Thank you, Surajit, for the introduction as well as for the invitation. It's really a pleasure to be here, even though virtually. And I'm sorry I couldn't. I was not being able to be here on a regular basis because of various engagements on Saturday in Paris. So, but it's always a pleasure to be here. So today I'm going to talk about extreme value statistics, so this is a subject which has very broad and interdisciplinary applications, ranging from engineering and climate science and finance on one hand, and all the way to in physics of disordered systems, random matrix theory, as well as number theory, and so on and so forth. And it's this interdisciplinary character which I find it very interesting. And we have been working for the last several years on this subject. So today I thought I'll just give you an overview and some perspectives on this subject rather than giving details of calculations and so on. So that's the so the talk is at more general colloquium level rather than sort of a specific seminar level. But if you are interested in details, you can ask me later. Okay, so let me just start just by giving a basic overview of what are the main. So what I'll pose is what are the main questions, what are the main observables, and what kind of methods one uses to go around it, and so on, and how statistical physics can be useful in this. So as you know, the extreme events are like earthquakes, typhoons, or tsunamis, or even the COVID pandemic that we are going through right now. These are rare events. They do not happen every day, fortunately. But when they happen, and if they happen, their effects are devastating. So it's, of course, very important to understand the statistics of such extreme events, in particular, the magnitude of such extreme events when they occur, the frequency, how often they occur, when do they occur, can we predict, and many other relevant questions associated with the extremes, which are obviously very important to understand, especially in these days. So no wonder this subject has been studied for a very long time, mostly in the statistics literature. There are standard books by Gumbel and many other people and so on. But then, this subject actually has found a broader applications in climate studies, in finance, economics, hydrology, sports, and more recently, in physics of physical systems like random walks, in disordered systems, random matrices, and all the way to mathematics and number theory and so on and so forth. Okay, so this is this very broad interdisciplinary applications, which makes the subject very interesting. So let me start with a very basic engineering application just to show you why the extremes are important. So imagine that you are a civil engineer and you are supposed to build a bridge or a dam over a river. Now, what you have at your disposal is the data, which is the height of the river for the last few hundred years. So what you see in this graph is the level of water on the Nile River in Cairo during 622 to 1284 AD. So this is the time series of the water level height. So you have these things, and this black solid line is just the time averaged water level. Okay. Now you are an engineer, so you want to know how high the bridge should be. So of course for you, I mean, this black solid line, the average height is not very important, because what is really important are these outliers. These objects where due to certain flood, the water level has increased quite a lot. So these are the extreme fluctuations, which are much more than the average, than the typical average value. And so your river height should be bigger than the typical value of these extremes. So you're not interested so much in the average, but you're interested in the typical value of the extremes. Okay. So therefore, it's very important to know that what is this typical scale of these big fluctuations rather than the average height. Okay. So this is the sort of very basic applications. Of course, you need to know the extreme statistics for this. And similarly, same question appears also in, for example, if you in the climate studies, if you are looking at the rainfall precipitation data for a number of days or some for a number of years from 1910, almost 100 years here. And so you see, this is the precipitation rainfall. And what you, again, there is an average, but what you are interested is actually these extreme fluctuations where, very sudden rainfall, which can lead to floods and things like that. And also, I mean, if it's a temperature time series, then these are, extremely high temperatures. And the global warming clearly is related to these extreme fluctuations, not so much about the average. Average might be flat, but the fluctuations might be increasing. And so they are very crucial to understand the global warming as well, these, the extreme fluctuations. So now let me just, so you can imagine, you can take any time series. You can take a financial time series, stock prices. Again, the extreme fluctuations are responsible for, financial crashes and so on. So it's very important to know. So basically, you can pose this question for any time series. Now, let me give you an example from physics now. So this is the physics of disordered system. So imagine that you have a quantum system, and on some graph, which can be a lattice or any graph, in fact, and with n sites. And so very generally, you can define the Hamiltonian of your system as in a site basis as Ij and Hij. Hij is just the matrix elements between site I and site J of your Hamiltonian, okay? Now, when we say disordered system, what we mean is really that these matrix elements Hij of your Hamiltonian, they are some random variables, okay? So this matrix, of course, has to be a Hermitian random matrix because this is just quantum mechanics. So you have an n by n Hermitian matrix. So for instance, I mean, if you just have, if you just have nearest neighbor interaction in site interaction, then this is Hamiltonian will be just a tridiagonal matrix. And this is the famous Anderson model that most of us know about. On the other hand, if you are thinking of a mean field model where basically all sites are connected to all other sites, so then, of course, you have a full n by n matrix, okay? And in this mean field model, you see, if you have a full n matrix, you have to first choose the matrix elements from some distribution. So the most common distributions that people study is what is called the Gaussian random matrix, which means that you take the matrix elements to be random variables, and the joint distribution, they are uncorrelated, and the joint distribution is just a product of the Gaussians. And the product of the Gaussians, you can always write this as trace of H dagger H if you choose the variance appropriately. And the whole point about this particular choice is that when you write this way, then you see that if you make a change of basis, that is, if you just rotate your coordinates under the rotation, the trace is invariant. Under any unitary rotation, the trace is invariant, and therefore this probability distribution does not change from basis to basis. And this property, actually, this rotational invariance, actually has a very important role in the analytical calculation of random matrix theory, and therefore has played a very important role since the time of Wigner, Dyson, and many others. And this is the famous Gaussian unitary ensemble of random matrix. So random matrix is basically this: you have just a Hamiltonian with random elements, independent entries, Gaussian entries, and so this is the joint distribution of the entries. Now, for each realization of the matrix, you diagonalize your matrix, and then you'll have n real eigenvalues, and these are your energy states, right? So lambda 1, lambda 2, lambda 3, lambda n. Now, what happens here in basic problem in random matrix theory is that even though the entries are independent random variables, the eigenvalues, they get correlated strongly because eigenvalues are complicated functionals of the matrix and entries, so they get very strongly correlated. And in fact, and then what you want to calculate is the ground state energy, which is the basic object in disordered system. So the ground state energy, that means for each relation, you find out the lowest eigenvalue. And then, of course, this lowest eigenvalue fluctuates from one sample to another sample. And you want to know how this, what is the distribution of the ground state energy. This is the first basic 0th question in disordered systems. And then you can go further. You can ask for the first excited states, second excited states, the gap between the first and the ground state and the first excited state, because they play a very important role in the dynamics of disordered systems and so on. So again, you see that here you have the minimum. So you are looking for the minimum of a set of random variables. So once again, this is the extreme value statistics. Okay, so it's a very, very basic way it appears in disordered systems. And so you see that, so this extreme, that means maximum or minimum of a set of random variables. So this is, sort of very abundant in many different problems. And we want to know what can we very generally say about the statistics of the minimum or maximum of a set of random variables, okay? So all these different problems, so can we just put them in some one general setting? So that's first question. And this is what I'm going to tell you now. How do we put all these different problems in one setting so that we can have a very general question? Sorry. So to do this, in fact, the general setting is the following. So as I said, so imagine that you have just a time series, xi versus I, and this xi may represent, for example, the rainfall or temperature time series, or the stock prices or height of a river, or even, for example, in the context of disordered system, you can think of this xi as the, or lambda I, the eigenvalue, and I is the sort of level of the energy states. So all these things, you can set it up like this. So you have a lambda I versus I, or xi versus I, in general, a time series, essentially. Think of this as a time series. And these entries of this time series are distributed in some way, which we often do not know, okay? So they are distributed in general from joint distribution P of x1, x2, x3, xn. Now, this information is, of course, not easily available. This is something you have to guess from your underlying data of that data available. So you have to construct what is how they are distributed, the joint distribution. They may be correlated also. And this is the sort of part of modeling of data, basically. Okay, so from the data, you have to figure out that what is the joint distribution of these variables. I mean, they may be independent. If there is no correlation between them, then this will just factorize. They may be independent, or as I said, they may be correlated also. Okay. Now, once you have this joint distribution, okay, so suppose that you give me this joint distribution, that's the first part, modeling part. And then you can ask several observables. So given this P of x1, x2, x3, xn, you can ask, first question to ask is, I look at, from a given sample, I look at the maximum of this set of n variables, max of x1, x2, x3, xn, or the minimum, which is the mean of x1, x2, x3, xn. So again, these are random variables. And what can I say about the statistics of the largest or the smallest value given the underlying joint distribution? So that's a sort of very basic question, okay? So given P of x1, x2, what can we say about the statistics of xmin? Can we calculate the statistics of xmax, xmin, mean variance distributions, knowing the underlying joint distribution of the entries? Okay. So the people who do data modeling, so they will give you the joint distribution, the statistics part, and then the physics part is that given this joint distribution, what can I say about the distribution of these extreme variables? Okay. Now, these are not the only questions. You can ask other questions. So, as I say, statistics of the global maximum, global minimum, but you can also ask at what time does the maximum occur, Tmax, okay? Or at what time the minimum occurs? Because they will also fluctuate from sample to sample. And you can ask what is the statistics of Tmax and Tmean? At what time, for example, the largest earthquake occurs? And then the aftershock, it will occur at some other time. And then at some point, it will become quiescent, and that's the minimum, and so on. And then in the context of disordered systems, you can ask order statistics. Order statistics means the ground state, which is the x min, and then the next excited state, second, third, fourth, maximum or minimum, whatever, either way. So these are called the order statistics. Okay, what can we say about the gap between these different excited states? So these are called order statistics, which are related to extreme statistics, of course. And then the last one is also what is called the record statistics. And this is also a very interesting subject on its own. So what do I mean by record statistics? So again, imagine that you have a time series data and you are given this joint distribution. So what do I mean by record? So as you all know, records are very ubiquitous. I mean, we're always talking about records in sports or records in temperatures and so on. So basically, record means a record happens at step K if the entry there, the value of the entry xk, is bigger than all the previous values, right? So we say this is so far this is the biggest. So this is the record at step K, okay? So in this figure, what you see is the red dots. So this guy, for example, the first guy is a record, and the second guy, by convention, second guy is a record because he's bigger than the first guy. Then the next guy, third guy, is not a record because his value is less than this. This is not a record, but this guy is a record because he's bigger than all the previous values. And then again, you have some periods of non-record, followed by another, when this record gets broken, and you get a bigger record, and so on. So the records, of course, the value of the records keep increasing with time. And you can ask many questions. So, I mean, if I go up to n steps, how many records are there? You know, how many records occur? In this example, you see there are 4 records, okay? So how many records occur? So there are also random variables. And what can I say about the statistics of the number of records? Okay? And then you can ask, you know, how long does a record survive? So if a record occurs and then it waits for a certain amount of time before it gets broken by another record. And this is the sort of age of the record. Okay, so what can we say about the statistics of the ages of the records? Okay, how long does the record survive? And these record ages are also important in many, many different fields. So for example, in the context of earthquakes, you know, this turns out that the record distribution, the size, you know, the inter-record time interval is exactly the size of an earthquake, the size of an avalanche in an earthquake. Okay, and they are usually power law distributed. This is called the, you know, Gutenberg-Richter law of earthquake physics and so on. So record statistics have been used extensively in many different areas. I mean, including earthquakes and, you know, growing networks, global warming, and so on. So, for example, I mean, just to cite you one example of of using record statistics, Sid Reckner and Mark Peterson, they wrote a very nice paper where they analyzed the data from Philadelphia and about the temperature records using the statistics of records. You know, what can you say about global warming and so on? Okay. Okay, so these are the sort of, you know, different. So these are the questions. So I have a general time series, and you know, let's say some statisticians have given me some joint distribution, and that's the modeling part. And given that, now the statistical physics part is that given this joint distribution, what can I say about the statistics of these various observables? That is the extreme value statistics, order statistics, record statistics, and so on. Okay. So this is the general question. Okay. So now let me sort of tell you a little bit about some models and the classical model, which has been studied for many, many years in the statistics and mathematics literature. And this is the case when there are no correlations between the entries of your time series. So that means your joint distribution factorizes into individual distributions. So P of xi, so each xi is chosen independently from the distribution little p of x. Okay. So these are uncorrelated variables. So in the context of disordered systems, this is exactly the famous random energy model of Derrida. So where you assume that your energy levels, which is your xi, x1, x2, x3, xn, you know, these energy levels are like this, your lambda 1, lambda 2 eigenvalues of the matrix. So it's like a diagonal matrix. And the energy levels, they are just completely independent random variables, uncorrelated. And the random energy model has played a very, very important role in disordered systems, because, you know, when you look at the real spin glasses and so on, so they are very complicated. Of course, you have all this kind of replica symmetry breaking and so on and so forth. But in this simple, very simple, uncorrelated model, you know, you can actually produce, you know, many qualitatively similar features as in real spin glass systems. So in that sense, random energy model has played a very important role in disordered systems. And for this very simple model, many things are well known now. And the distribution of X max and X min, and the T max and T min, order gap statistics and record statistics. I'll not go through all these things. I'll just show you a little bit, because it's very simple how to calculate the statistics of X max and X min. So I just want to show you just to take you through this little exercise. It's very, very you know, simple, extremely qualitative, extremely simple example. So what is this problem? So the problem, we have this joint distribution is factorization. So you have given me this little p of x, and I want to calculate the statistics of the maximum, let's say, okay, max of x1, x2, x3, xn. So this is a random variable. How can I calculate its distribution? So the key thing is to look at the not the PDF, but look at the cumulative distribution. Okay. So cumulative distribution of the maximum. So I'm asking, what is the probability that the maximum is less than some number w? Okay. So this is, I would call it Qn of w. It's a function of n, and of course this w, right? This is the probability that your maximum is less than equal to w. Okay. So now immediately you realize that this is nothing, because if the maximum of a set of random variables, if it's less than w, clearly, you know, each of them has to be less than w. That's clear, right? Because I mean, this is necessary and sufficient. Okay. So then what happens? Just 1 second. Sorry about that. So this is the joint distribution. So the probability that, so this event is same as the probability that each of them is less than w. So then, since they're independent, so they factorize. So this is just nothing but the probability that any one of them is less than w to the power n, which is just this integral minus infinity w to the power n, which of course you can write using normalization as 1 minus w to infinity to the power n. So this is the exact result for any p of x. Okay, very simple. Okay, but this exact result, what do we learn from this? I mean, in physics, I mean, we always looking for universalities. So for instance, I mean, when we are looking at the sum of random variables instead of maximum, we all know about central limit theorem. That is, no matter what the individual p of x is, when you take a sum of random variables, if the second moment of each of the p of x is finite, you know that the sum always converges in the large n limit to Gaussian distribution. This is the statement of central limit theorem. Okay. So question is there any sort of central limit like theorem here for the maximum, not for the sum, when I take the large n limit? Okay. And for large n limit, this formulation is very important to 1 minus this, because what happens in the, if you have to take the n large and you have to take this w large so that this is small. And if this is small, you can just exponentiate it and you can derive the scaling form of this distribution. Okay. And indeed, it turns out, like the central limit theorem, there are interesting scaling forms here. So basically, in this limit, when n and w both are large, you see that you can show that this actually converges to some distribution. This is a cumulative distribution, of course, which is w minus an over bn. So this an and bn are, depends on the details of this p of x, or the, but it turns out that the scaling function, okay, this is universal in the sense there are only 3 possible varieties. Okay, unlike the sum of random variables where you have only one possibility, which is Gaussian distribution, this scaling function. Here it turns out there are 3 classes. Okay, and these 3 classes depends on the tail of p of x, and these are what are called the law of extremes. Okay, so I'll show you in a minute what are the tails. So this is exactly like law of averages. Here, this is the analog of the law of extremes. And, this has been studied from almost 100 years, starting with Frechet and then many other people's in mathematics and statistics literature. Has many applications, as I said, random energy model of Derrida in the disordered systems. And so what are the three distributions, 3 universality classes, fixed point distributions as you increase n? So first thing is that if p of x has a faster than power law tail, for example, if it is an exponential or Gaussian, this p of x, then it turns out that the scaling function in the large n limit of the maximum, it converges to this particular form. This is the cumulative distribution. So it goes from 0 to 1 as z increases. And this is what is called the Gumbel distribution. Then if p of x happens to be a power law distribution as a power law tail, then it converges to some maximum distribution, converges to something called Frechet distribution. And if it is bounded like uniform distribution, it converges to something called Weibull. Don't pay attention to the details of these functions, but basically, if you plot them, plot means you plot the derivative of them, which is a cumulative, so derivative is the PDF. So the PDF of the scaled maximum in the large n limit converges to only one of the 3 possible classes. So no matter what p of x you start with, you will flow to one of the 3 fixed points, okay? Either Gumbel, Frechet, and Weibull, depending on the tail of px. Okay? So this is the law of extremes. And and it's quite non-trivial, this to prove no matter what p of x is. It's very simple to analyze. You just have to, as I said, just analyze, you just exponentiate this guy and put the behavior of the tails and you get these results. It's trivial actually. But it's quite interesting that there are only 3 possible classes. There is no other extra classes for, typically any p of x you take. You will flow into one of the 3 fixed points of this extreme classes, basically. Okay. So this is all very well understood when there are no correlations between the random variables. Okay. So the question is, and this is where our interest was, that in most realistic systems, of course, these random variables are correlated. So, for example, if you look in the temperature time series, if you have a hot day, one day, next day, most likely it will be pretty hot also. So, there are strong correlations between these, these random variables. It's not that they are uncorrelated. Okay. So then the joint distribution, it doesn't factorize. Okay. So in that case, what can we say? I mean, this is the sort of, so there the extreme value statistics is highly non-trivial. And this is so there is one case where you can make some progress using some kind of renormalization group arguments from statistical physics. And this is the following. So imagine that you have a weakly correlated random variables. By weak correlation, I mean that these xi, xj variables, they have an exponentially decaying correlation function, and with a correlation length psi, which is much, much less than your system size n. Okay. So if that happens, then you can do a sort of block argument a la Kadanoff. So you can break your system into blocks of correlation length psi. Okay. And so you have this time series, and you are interested in the global maximum, which is this guy here. Okay. But once you have broken into blocks, and suppose that from each block, you identify the local block maximums. Okay. So the global maximum, which is the maximum of everybody, is also the maximum of the block variables. Okay. Block maximum, Z1, Z2, Z3, etc. Okay. But the point is that this block maximum, they belong to different blocks. So they're essentially uncorrelated. Okay. So I don't know what the distribution of each block maximum is, but all I know is that these guys, they are essentially uncorrelated because they belong to different correlation blocks. Okay. So again, I can then invoke the independent variable theorems, even though I do not know the P of Z, individually, but I can guess from numerics and find out its tails. And then I know that it will go to one of these three classes, Frechet, Gumbel, and Weibull. Okay. So when you have weakly correlated random variables with a finite correlation length, basically you go back to the independent class for the extreme statistics. However, this will break down when the correlation length is very large compared to the system size. So this is a strongly correlated system. Okay. So for strongly correlated random variables, when the correlation length is order, we can no longer use this argument, and we have to find some other way. And there, the extreme value statistics is extremely hard, and there are very few exact results. And so our main interest is actually in the extreme value statistics in the strongly correlated systems. Okay, so this is the area which we have been working on for the last several years. So I want to tell you a little bit. I won't go into the details. I just want to give you some flavor. I mean, what kind of systems we look at and what kind of questions we ask. So this is the subject, basically extreme value statistics in strongly correlated systems. And so what is the key idea? I just want to give you some key idea. So the key idea is to sort of use tools from statistical physics, okay, to deal with this problem. What do I mean by tools from statistical physics? So the point is the following. So you have you have a set of random variables x1, x2, x3, xn, and you have some joint distribution, and you want to know the distribution of the maximum. Okay. So once again, as before, we look at the cumulative distribution of the maximum, that the probability that the maximum is less than or equal to some W. And as I said, this is very general, correlated or not. It's always true that the probability, if the maximum is less than W, that means it's the same event as each of the variables must be less than W. The only difference is that now we can no longer factorize it. Okay. But the point is that if I know the joint distribution, so this object, this cumulative, joint cumulative distribution, this is just a multiple integral, right? So I have to integrate over all the variables, but it has to be less than W. So I integrate them from -∞ to W. Okay. So this is so basically the main problem is that if you give me the P of x1, x2, x3, xn, all I have to do is an n-fold integral. That's all. Okay. Problem is this is not factorizable. Okay. So how do we deal with these multiple integrals? But here comes the statistical physics, because you immediately notice that the following, that I can always write down any function p as e to the power minus log p, right? Just as trivial thing, e to the power minus log p. So I can cast this as e to the power minus e of x1, x2, x3, xn, where this e is this minus log p. And you can interpret this e then as the energy of a strongly interacting gas of n particles whose positions are x's, and they are confined between -∞ to W, right? Because the integrals go from -∞ to W. But then you see that this is e to the power minus e integral. So this is nothing but the partition function that you're all familiar with in statistical physics. So basically, if you give me this p, I'll just compute minus log p, that will give me the energy. And then all I need to compute to calculate the cumulative distribution of the maximum, this is just the partition function of a gas which is confined from -∞ to W. So the new thing is that you have a hard wall at W, okay, because your integrals ends there. And then basically you want to calculate the partition function in the presence of a hard wall at W, okay. But, in statistical physics, we have, many different tools to deal with statistics, to partition function, okay. And so that is exactly what we do. In different problems, we first identify the P of x1, x2, x3. From this, we identify the energy. And then from that, we have to calculate a partition function, and we can use very different methods. So let me just show you what happens, why the classical problem of uncorrelated variables is trivial. Because you see that what happens there, if you have a factorization property, this IID case, okay. So that means that energy just minus of log of capital P. So this means it just breaks into sum minus I equal to 1 to n log of P of xi, okay. So that means there is no interaction between these particles. So it's a non-interact, it's an ideal gas confined between minus infinity to W, okay. And so ideal gas, so therefore, and the energy is just log of this little of P of x, and this gas is totally non-interacting, and that's why, I mean, ideal gas, we all know it's trivial. I mean, so partition function is just its individual partition function to the power n, and that's why it was very easy to solve the non-interacting case. And what happens with the strongly interacting gas is that there is no factorization, and as a result, so you have this, it's a strongly interacting gas of particles, okay, and confined between minus infinity to W. But as I said, there are many, many different tools which are available to us from statistical physics, either exactly solvable models, large n, saddle point method, path integrals, when they are continuous variables. You can have mean field theory, renormalization group, large deviation theory, and many, many other tools. And so using these tools, we can actually, make some progress on the distribution of the maximum for strongly interacting random variables. Okay, so that's the sort of key idea. So after that, I mean, I'll not give you any details, but basically this is the main idea. I mean, if you have this, and it's very simple, but this is the sort of generic main idea. Okay. So what I'll do now, I'll just give you very briefly an outline of 4 different types of physics problems that we look at. So one is this, what I call the real space condensation in mass transport models. Okay, I'll explain to you what these problems are. And then Brownian motion, random walks, Levy flights, and active particles these days. Then random matrices with many, many different applications. And then the stochastic search process, which is a lot of applications in computer science. Okay, again, I'll not go into the details. I mean, for each area, I'll just give you, just very briefly, what is the sort of basic problem. Okay, so let me start with the mass transport models. What do I mean by real space condensation? So I'll start with an experiment which was performed in a shaken granular gas by Vandermeer et al. So basically, imagine that you have a box, like in one-dimensional box, for example, which is divided into different compartments, and you have some granular balls, like pith balls, for example, light balls, and some fixed number of particles, balls, and these compartments, there are holes which connect between 2 adjacent compartments. So these balls can go from transport from one box to another box. So this is the mass transport, if you like. And for simplicity, this is in their system, they had a kind of periodic boundary condition. That means if it leaves here, it basically enters to this box. Okay. And then what you do is you take this system and you vibrate, okay, with some frequency and amplitude. You vibrate this box. So these balls are just, shaken. And then once in a while, they go from one box to another box and so on. So the actual physics is quite complicated. I'll not go into the details of this. But you see that there are many parameters in this model. So one is this, you have this number of particles. Then you have this, temperature. And you have this vibration frequency and amplitude. You have the height of these holes and size of the holes and many, many different parameters. So what happens, what they found in the experiment is that when you shake it and then, you wait for a long enough time, and then the system reaches a stationary state. And of course, you have a conservation law here, which is that the total number of particles is conserved. Okay? There's no particles are not disappearing from the system. So you shake it for a long time. And then depending on your parameter space, in some parameter space of your problem, when you look at the stationary state in the long time limit, what you see is the following. What you see is that there is a condensation. That means a large number of balls, they condense into one single box. And this single box is spontaneously chosen. So you have, of course, a translational symmetry, but this translational symmetry is spontaneously broken And one of the boxes is chosen in the long time limit. One of the boxes is chosen where a macroscopically large number of particles condense. So this is like the Bose-Einstein condensation that we are all familiar with. But in Bose-Einstein condensation, the condensation happens in the momentum space, or energy space. I mean, some energy levels like ground state gets populated by a macroscopic large number of bosons for dilute bosonic gas. But here it happens in the real space, okay, in the stationary state. So the problem was to understand how do we characterize this condensate, how many particles are there in the condensate, and so on, and when do we have condensate and things like that. Okay, so this is a very big subject. I'm not going into the details of this, but you can ask, where is the connection to the extreme value statistics? And the connection is the following. So you look at the number of particles in each box. So this is your basic NI variables, which is exactly like the XI or entries in time series. So think of this as I, and this is NI versus I. So then you see that the number of particles in the condensate is nothing but the maximum, right? If there is a condensation, then this one single guy which has the largest number of particles. So you're looking for basically the maximum of the maximum occupation number, right? The site with the compartment with the maximum number of particles. So again, you are looking for the max of these random variables N1, N2, N3, Nn. So all you have to know is what is the joint distribution of these variables in the steady state. And it happens that, that in this case, you can actually calculate the stationary state, and they are strongly correlated because of the conservation law, because the total number of particles is conserved, which makes them very strongly correlated. And I'll not go into the details, but basically you can calculate this joint distribution of the occupation numbers. And from that, you can actually compute the distribution of extreme statistics, again, by using the technique I said, you just calculate the partition function from minus infinity to W. And from that, you can extract what is the distribution of the largest one. And that gives you a complete characterization of the condensate in this problem. Okay. So this is sort of an area which I've been working with various collaborators. So I'll not read out all of them in detail. And then you can ask, what happens, are there other applications of this? In fact, it turns out this condensation phenomena is quite common. It appears in many, many different areas. So, formation of clouds and formation of polymer gels. Polymer gel, one big gel which forms, which is the analog of condensate. Or on the surface growth problem, you have a big atomic cluster. So with Mustansi Barma and Supriya Krishnamurthy, we had worked on it for quite a long time. And then you have these traffic models where, when a big traffic jam occurs, that's the analog of the condensate, basically. And again, you can use exactly the same extreme value statistics there. Then condensation in growing networks. When you have networks, growing networks, you have this, formation of hubs. One big hub like Google can form, which has a giant component, and that's the analog of the condensate. And then it happens in active particles, run and tumble particles, for example. You can have a giant run of a bacteria, and so on. And then it also happens in discrete nonlinear Schrodinger equation, where you have a localized wave function, which is the analog of the condensate. So the extreme value statistics also has applications in all these different areas. Okay. So let me now quickly tell you about random walks and Levy flights, because this is something that is very simple. So imagine that I have just a very simple one-dimensional random walk. So it starts at the origin. So Xi is the position of a random walker after step I. So random walk means that, the previous step position increments by drawing a random jump variable. So this is and these jumps are independent random variables. And let's say you draw from a symmetric P of eta. Okay. So then, and if it is in continuous time, it just becomes Brownian motion if the variance of this jump distribution is finite. Then it converges to a Brownian motion in the long time limit. But if the variance of this jump distribution is infinite, like it has a power law tail, then this is this famous Levy flights. Okay? So this mu is called the Levy index. So when I say random walks, Levy flights, I mean more general random walks, basically. Okay? So then, so this is a strongly correlated problem again, because even though the jump increments are independent, uncorrelated, but you are looking at the position variables, and the position variables are strongly correlated because they are sum of the increments, so they are actually strongly correlated. In fact, the joint distribution of the position is just the product of the increment, but you see that this is not factorized into Xi, it factorizes into the Xi plus 1 minus Xi. So they are still very strongly correlated. Okay. And you can ask, what's the distribution of the extreme displacement, maximum displacement of this random walk? Okay. So this is the, so you take your sample, your time series, and then you look at the maximum, and you ask what's the probability distribution of this maximum. Okay? So again, the object to look at is the cumulative distribution. Probability that the maximum is less than or equal to some W is precisely the probability that all the xi's are less than W. That means the probability that this walk did not cross this level W. So this brings to another very classic problem in statistical physics and probability theory, which is the problem of survival probability or first passage probability or persistence problem. And this is the first passage problem. That is, the first passage means when is the first time you cross this level, but survival probability means that probability that you do not cross this level up to step n. Okay? So this is for Brownian motion. This is very easy to compute. You can just use Fokker-Planck approach with the absorbing boundary condition. But for Levy flights, it's a much harder problem. And there have been a lot of progress on this, and we have worked quite a lot on this problem, and with various collaborators, and it has applications in fluctuating interfaces, chemical processes, and again finance, because in finance this is like a stock price, if you like, and in ecology and so on and so forth. But again, the same idea, basic idea is similar. I mean, you have to find out the joint distribution and calculate the partial function in some sense. So let me just mention very briefly the sort of very recent work that we have done. So this is about active particles. So, passive Brownian motion, all of us are familiar with. This is the famous Einstein Brownian motion, which is that you have a, pollen particles like this yellow particle here, and it's inside a liquid, for example, and the liquid molecules, which are just doing random motion. And this particle does not have any inherent motion on its own. That's why it's called passive. It moves because the other molecules of the gas around it come and hit it randomly. So it imparts a random collisional motion to this yellow particle, and then it moves randomly. And that's the classic Brownian motion. Okay. Now, on the other hand, in active particles, what happens, like E. coli bacteria? So E. coli bacteria has this structure that it has a flagellar tail, and what happens is that these tails give us a directional motion, and if the tail are this way, the tails are this way, it moves in the opposite direction. Okay. And so it moves ballistically along a straight line. And then what it does, it sort of orients this flagellar tail. And by orienting this flagellar tail, it can change the direction. Okay? And then it sort of moves in a different direction and during an exponentially distributed time. And then again, it changes direction and so on and so forth. Okay? So this is the famous run and tumble model of active particles. So here,
Satya,
yes.
one second.
Yes.
So does it change the direction because of itself or because of the interaction with the surrounding?
No, it changes on its own. It's totally autonomous motion. Okay. It changes on its own because it's searching for food. So it just changes the, it was trying to go in one direction. It didn't find the food. So it said, okay, let's try to explore another direction. So then it changes its orientation and moves in another direction. Okay.
Okay. And then regarding passive Brownian motion, there is also there is also external forces present, right? So you are taking that into account.
Yeah, no. I mean, this is just a plain Brownian motion, a la Einstein. There's no potential, no other force. I mean, you can add all these complications if you want, but this is a 0th order model, if you like. Okay.
Fine.
So in the active particles, so therefore you have this ballistic run followed by random orientation change, which happens with some rate gamma in rate gamma, rate of change of the orientation, which is basically essentially the typical lifetime, mean time of the run time, basically. And then you also have another parameter, which is the WV. That is, when you change the direction, you choose a new velocity and the new speed, basically, and you choose from some distribution. Okay? So these are the two parameters, the tumbling rate and the WV. And you can ask again these extreme questions, that is, what's the maximum displacement of these active particles? Okay. So I'll not go into the details, but I mean, we have recently solved this problem exactly. And it turns out there are many interesting properties of this system. So for example, if you look at the minimum position of this particle, the minimum or maximum doesn't matter, and you ask, what's the survival probability? What's the probability that the minimum is bigger than 0? That means it doesn't cross the x equal to 0 hyperplane in d dimensions. So it turns out that this is totally universal. It does not depend on dimension. It does not depend on these WV and other parameters and so on. And very interesting universal survival features. And this is related to some theorems in the probability theory, which is called the Spar-Anderson theorem. So I'll not, again, I don't have time to go into the details, but this is a sort of recent work with my PhD student, Francisco Mori, and in collaboration with P.L. Edusal and Gregory Sher. And
but
so
Satya,
again,
there should be some scale at which you will not be able to actually differentiate between the spreading of wings of this particle.
Of course,
right? Yeah.
Of course, and the long time limit, the active particles, they behave like the Brownian motion. Okay?
Exactly, that's what I thought.
But there's a time scale gamma inverse, as I said. When time is much less than gamma inverse, you have ballistic motion, you have activeness, and when time is much bigger than gamma inverse, it converges to Brownian motion in the long time limit. Okay?
Fine.
But there are fingerprints of activity even at late times, depending on what observable you are looking at. Okay. So this is the random walks and Levy flights, and very briefly I'll talk about just a few slides about random matrix theory, and just to tell you again what are the questions and what are the sort of interesting results. Again, I mean, I'm not giving you any details of all these results, because this is a very general talk. So as I said, I mean, I mentioned briefly the random matrix theory. So essentially you have this Gaussian Hermitian random matrix H, and you diagonalize, you get the n eigenvalues. And as I mentioned, that the n eigenvalues, they are strongly correlated. Okay, so you need to know what is the joint distribution of the eigenvalues. Unfortunately, this was already computed by Wigner and other people before him. So this is known. So for Gaussian random matrix, using this rotational invariance property, you can actually compute the joint distribution of the eigenvalues. And this turns out to be the following. So first, you have a term which is exponential minus n/2 summation lambda is squared. Okay. And then you have another term which is product of lambda j minus lambda k squared. Okay. So this is the part which comes from the Gaussian distribution of the entries, but there's an additional part which gets generated because these are eigenvalues and not the entries themselves. And so when you derive the distribution, there's a technical part, there's Jacobian involved, and that gives you this extra term. So, but this extra term is very important, because what happens if you did not have this extra term? Then you see again the joint distribution, and this is just a normalization constant. So if you did not have this extra term, then again, this is just a factorization. So it's just a NIID Gaussian random variables. So again, the distribution of maximum or minimum will be like Gumbel distribution that I talked about already. So this is this extra term which gives rise to the correlations between the eigenvalues. Okay, and in fact, you see the eigenvalues of random matrix, they are strongly repelling. This says that when the probability that two eigenvalues are very close to each other goes to 0, that means the eigenvalues repel each other. This is the famous eigenvalue repulsion in nuclear physics, because the nuclear spectra, they are exactly distributed by this kind of GUE matrix and joint distribution. And this is exactly the origin of the eigenvalue repulsion in nuclear physics. Okay, and you see that because of this term here, it's called the van der Monde term. These eigenvalues get very strongly correlated. Okay, so yeah, so these van der Monde terms get strongly correlated. So now, if I am interested in the ground state energy, that is the distribution of the minimum eigenvalue, or because they are symmetric, you can also ask the same as the distribution of the largest eigenvalue. And this is a subject which has created a lot of interest in both physics and maths literature in the last 10-20 years. And you see, again, I mean, once I know this joint distribution, this is a perfect example of what I've been talking about. So this van der Monde term, I can always write as exponential of log. And when you do that, you see you have a gas of particles. Again, you can think of this lambda i's as the positions of a particles on a line, and as eigenvalues. And its energy, if you like, has two terms. So there is this term here, lambda I square, which is like an external potential, right? All these particles, they are sitting in an external confining harmonic potential. But then there's an interaction term which comes from the van der Monde, and this makes them strongly correlated. This interaction term says that each pair of eigenvalues, they repel each other with a minus log interaction, log of lambda j minus lambda k. So this is like the charge is like a Coulomb repulsion in 2 dimensions. So these are, of course, real eigenvalues. So they are sitting on a 1-dimensional line, but they're repelling each other pairwise by a 2D Coulomb repulsion. Okay. So this is the famous Dyson log gas. Okay. So this repulsion makes them strongly correlated. So what happens here? This guy. So in the large n limit, so you are looking for for example, you want to minimize this to find out the ground state configuration. And what you see is that, the potential energy is trying to minimize the eigen. So they'll try to push all the lambdas towards the center of the potential well, harmonic well. But then there's repulsion. They cannot come just on top of each other. So there's repulsion. So they'll try to spread them. So there's a competition between these two terms. And as a result, the eigenvalues will, settle over a finite region in space. And the distribution of the density is the famous Wigner's semicircular law. Okay. So this is very well known in random matrix theory for many, many years. But what is interesting of late is to calculate the distribution of the largest eigenvalue or the minimum eigenvalue, ground state energy, if you like. And as I said, the cumulative distribution of lambda max is just this integral, multiple integral, right? Probability that all of them are less than W. So you have all the eigenvalues. So you have to just put a hard wall at W and you ask, what is the probability that all the eigenvalues are less than W, okay? And it turns out that this particular case of random matrix, Gaussian random matrix, you can actually compute this integral exactly in the large n limit. And this gives rise to what is what is very celebrated, is called the Tracy-Widom distribution. So Tracy and Widom are two mathematicians and from California. And what they showed is that this multiple integral, when you analyze it in the large n limit, then it converges into a scaling function which is a function of W minus root 2, meaning that the largest eigenvalue will be at the edge, which is around root 2. Because, you see the largest eigenvalue on an average will be at the edge of the Wigner's semicircular law, which is root 2. But it has a fluctuation, very small fluctuation around it, which is of order n to the power minus 2/3. And when you scale it, it becomes a unique scaling function, f2 of z. And its derivative, it has a non-Gaussian tails. Okay, so it's not Gaussian. It has exponential minus mod z cube as z goes to minus infinity. It falls very fast. And on the positive side, it goes to z to the power 3/2 exponential. So this is a non-Gaussian, and also it's not like Gumbel for uncorrelated variables. So this is one example of a strongly correlated system where you have a scaling law for the distribution of the extreme, which is very non-trivial. And once this Tracy-Widom distribution were found, after that, it's amazingly, this Tracy-Widom distribution has been found in many, many different physics area problems, in directed polymers, in growth models, in the KPZ equation. If you look at the KPZ Kaiser-Pariser-Zhang equation, and if you look at the height distribution, this is exactly given by this Tracy-Widom distribution. In large and gauge theory, in liquid crystals, spin glasses, it's a subject of different talk. I will not go into all these details. It has been, verified in measured in many different experiments in turbulent liquid crystals, in coupled lasers, optical fiber lasers, in disordered superconductors, and many examples. And if you're interested in this, you can look at these two very nice popular articles. One in Nature Physics by Mark Buchanan, the equivalence principle, and the other is by Natalie Olchover in Quanta magazine. So one of the interesting questions we are interested in, that why is the Tracy-Widom law so ubiquitous, so universal? It appears in so many different areas in physics. And so we have worked quite a lot on that. I'll not, I'll skip the details here. So it turns out that Tracy-Widom is just a typical distribution, okay, like central limit theorem Gaussian, but it has a large deviation tails, and these large deviation tails are universal. And not universal, I mean, large deviation tails are actually, it's like a phase transition. So when you take the large n limit, so if you look at the distribution of the ground state energy, so you see that there's a peak, and the peak is given by the Tracy-Widom distribution with a width which is n to the power minus 2/3. But then there are these extreme tails here, okay? And these tails have this large deviation property, it's e to the power minus n square into some function phi minus, and on the right side, it's e to the power minus n phi plus. So what happens is that these atypical rare fluctuations of the ground state energy, they're not described by Tracy-Widom, but they're described by this large deviation function. As you increase n, what happens is that this region here, its width decreases like n to the power minus 2/3, so it becomes extremely narrow. And then you have just, these, basically the tails take over. And these tails they are like the free energies of two sides. So this is called the strong coupling phase, and this is weak coupling phase. And this becomes a critical point. And there's a third order phase transition between this critical point. And so the point we try to make is that the Tracy-Widom distribution is universal because you can sort of associate it as a universal crossover function across a critical point. And this critical point is a third order critical point, not the usual second order critical point that we are familiar with in critical phenomena. This is a third order critical point which appears in gauge theory and so on. And here it's exactly similar physics. And these two phases on the left and right are very different. In fact, the left phase means what? Means that you are looking for fluctuation, deviation of the largest eigenvalue much less than its typical value. That means you're pushing the gas, your wall, very much to the left, you're pushing this gas. So this is the pushed phase. This is what is called the strong coupling phase. And on the other hand, pulled phase, meaning that if you're looking for the fluctuations where the largest eigenvalue is much bigger than the rest, you're just taking one charge out of the Wigner semicircle and putting it outside the Wigner semicircle. It's like taking a Fermi out of a Fermi C, just one fermion out of a Fermi C. And so this is called the pulled phase. And these two phases, they are separated by the phase transition exactly at the edge of the Wigner semicircle. And so the traceoidom is universal because it's associated to this critical point in the sense that, you know, we know that the crossover functions across a critical point are often universal. Anyway, I'm sorry, I could not give much details about it, but if you are interested, we wrote a nice review article on this third order phase transition with Gregory Sher, which is available in the literature. So just one slide about search process. So search processes are ubiquitous in nature, you know, data search in Google that you know, or protein searching for a, you know, binding site on a DNA, animal searching for food, you know, foraging period and so on. So in search problems, so typically what you do, that you have a cost function which you need to minimize. Okay, so again, so therefore, I mean, you are always trying to optimize different search strategies. So basically what is the point? You come up with an algorithm for a search algorithm, and you associate some cost function to it, and then try to minimize this cost function. And this minimization, again, links it to the extreme value statistics. So for instance, I mean, very recently we came up with an algorithm, which is called the stochastic resetting problem. Stochastic resetting means that if you are, let's say you are doing, trying to search a target by random walk, if you just search randomly by plain random walk, you know, the mean time to find the target is usually in one dimension, for example, is infinite. Okay, so what you do is you know, once in a while with some finite rate, you just come back to your starting point and restart the search. Okay, so this is what is called the stochastic resetting, and the rationale is that because you start a new search, you know, you probably explore a new pathways. You'll not get stuck into a metastable state, and you will explore new pathways. And maybe you will find your target much more easily. And it turns out that this is a very efficient search algorithm, this resetting. So this is a sort of, you know, the search algorithm that I introduced with Martin Evans about 10 years back. And it has now become very popular. And so here again, the cost function is as the mean first passage time to find the target. You want to minimize the mean first passage time with respect to your parameters of your search algorithms. And then this is the, again, the extreme value statistics, you know, plays an important role here. Okay, so let me just summarize. So essentially what I talked about, you know, extreme value statistics basically in two steps. So first step is that given your data, your time series or whatever, you know, you have to first estimate what is the joint distribution. This is usually done by statisticians, but these days a lot of data science people are also working on it. And so you have to have some idea about the correlations, and from that you have to estimate somehow the joint distribution. Okay. Once that is done, then second part is the physicist's job, the statistical physicist, which is that given this joint distribution, what can I say about the distribution of the extremes? For example, the distribution of the X maximum. And there I said, you know, this is exactly like calculating the partition function of a gas in a confined geometry minus infinity W of a strongly interacting gas. And we have many tools in statistical physics to deal with this. The basic problem is this, estimating this multiple integral, okay, n-fold integral, and extract the information about large n limit. Okay, so the main goal is to understand for strongly correlated variables, are there sort of, you know, universal distributions? What are the universality classes? What can we say? We are not there yet. I mean, right now we are at a stage where we're trying to, you know, solve different models and try to get a general idea of different universality classes in extreme value statistics, okay, of strongly correlated variables. So So to conclude, so basically, I mean, I find this is very exciting and rapidly evolving, sort of very exciting area of research, which is also rapidly evolving, and mainly because of its, as I said, because of its very multidisciplinary applications. On one hand, you have statistics, geology, finance, epidemiology, engineering, all the way to disordered systems, random matrix theory, gauge theory, cold atoms, and so on, and even in number theory and mathematics. So this is really, very, very exciting, and so many different connections. And it's really, I mean, I really find it really absolutely fascinating. And so we wrote a recent review article, so it's a sort of pedagogical review on this extreme value statistics of correlated random variables, in which just appeared in physics reports, in case you are interested. So let me acknowledge all my students. So the ones in red are the current students, Francisco Moria, Anna Flack, Benjamin De Bruyne, and Pierre Marni, and all the ex-students and postdocs and various collaborators at Orsay. And also I had the fortune to collaborate with many, many people outside Orsay, outside France. And of course, many of them made many, many important contributions to the development of this field. And so I'm really grateful to them. So thank you very much for your attention.
Thank you, Satya, for a truly fantastic presentation. We are open for questions, so please feel free to ask questions.
Shall I take off the slides?
No, you can probably leave it on for a bit in case you have to refer to it.
May I make a question, Surajit?
Yeah, please go ahead.
Yes, I would like to ask you the following. If you consider your time series as being given, say, by the logistic map, and and you are in a region where the Lyapunov exponent is positive, therefore the correlation is rather weak, and the basic theorems that you presented in the beginning are applicable. Yes. My question is, what happens at the Feigenbaum point where the Lyapunov exponent is 0?
That's a good question. I don't know. We haven't looked at this actually. That's a very interesting, because that's a point which is a sort of marginal point where probably the correlation length just starts becoming large or something, and the growth is non-exponential. And so I don't know. I mean, I don't think there has been any study of the extreme statistics there. I've not seen in the literature, at least.
Okay,
that's an interesting point. Yeah, problem. Yes.
Thank you.
Can I ask a question?
Yeah, go ahead, Pragya.
Yeah, my question is like, it's a technical question. Satya, like I'm always confused about, like I have not seen anywhere mentioned, like the statistics at extreme value is not distribution at the extreme value is not same as the ensemble averaged density of states at that value, right?
Yeah, because No, because I mean, you see, there are two things one has to separate. So one thing is that you can actually look at the density of for example, your disordered system or something. You can look at the density and the global density, and you can look at the tail of the global density. Okay, the extreme tail of the global density. Now, extreme tail of the global density, that will give information about the average of the extreme value. It will not give you the fluctuations of the extreme value. Like, as I said, for example, in random matrix theory, I mean, if you look at the Wigner's semicircle, which is the average density, at the edge of the average density, that gives you the mean value of your extreme observable, okay? But it does not give you the fluctuations of the extreme. And the reason is because, when you look at the average, when you take the large n limit, so it already, pins you to the mean value. Because the outside your finite finite support, the density goes to 0. I mean, which you have thrown away all the information about the fluctuations of the extreme there. Okay. When you look at just the density, it gives you information only about the mean of the extreme, but not about its fluctuations.
Okay, so there is no, like, you have not thought of, because as you know, like, I don't have to really say this, everybody, each one of us knows that how important it is to know the density of states at ground state, let's see.
Yes.
Okay. Yeah. And so, like, you have worked so much on these extreme value statistics, like, is there,
Yes.
like, is it very difficult then to connect the two? Because I know that Mehta has
no, this has been, this has been, well, connect the two means that you can, you can guess something about the extremes from the density, but not everything. That's all all I'm saying is that you see extreme value statistics. I mean, you see this program, right? So this it contains informations about multiple variables, right? Joint distribution.
Yeah.
Now, density is a 1-point function, so obviously density cannot contain all the informations, right? So this is the point. So this is the point. So so it actually carries a much more information than the 1-point function.
Yeah, I have a question, Satya.
Yeah, go ahead.
Yeah, sure.
Yeah, see, you talked about these probability distributions which are not factorizable and the ones which are factorizable.
Yes.
So that sort of appears like, non-entangled and entangled kind of systems. So do you think extreme value can throw some light on entanglement?
Yes, of course. I mean, in fact, we have actually worked quite a bit on this entanglement entropy in the context of random matrix, because if you take a random pure state, you can actually, map it to random matrix theory, and you can compute the entanglement entropy of these things. And in fact, using these extreme statistics, you can say quite a bit about the, the entanglement entropy. I mean, so for example, one of the basic conjectures in many, unfortunately not correct conjectures, is that people often say that if you take a pure state which is totally random, and then this is a maximally entangled state, okay, and this is a statement which is on the mean, on an average it's true, but when you look at the fluctuations, that means if you ask what's the probability that a randomly chosen pure state is maximally entangled, it turns out that the probability is actually very small. Okay, so the statement that a maximally a random pure state is maximally entangled is not entirely correct.
Okay. Thank you.
Okay, you Man, you had a question.
Yeah, I have two questions. One is a very practical question, and since the question is about a time series from the heart rate or from the EEG, my question is the following.
From what? Time series from what? Sorry, I didn't catch your last sentence.
The brain signal.
Okay, brain signal.
Yeah, okay. Or the heart. We try to analyze those two time series. My question is the following. Suppose you have a time series, right? N equal to 10 to the million. No, million terms. Suppose I window the thing for 1,000 time point, right? Then if I determine the joint distribution of this, right? Then suppose I window the thing, I slide the window across the whole time series.
Yes.
Is there any way from the generated statistic calculate the change of the probability, joint probability distribution? Because
so this is because I understand. In fact, if your original time series is stationary time series, then of
it's
course
a non-stationary
window. Yeah, so in your case it's non-stationary. So in that case, unfortunately, you cannot say anything about the future just by studying the current block. You have to really see how it grows. Sometimes of course what you can see. Sometimes what you can see is that it depends on really the correlation structure present in your data actually. So
one thing when we try to analyze the EEG time series, the first step we do is to detrend it using the multifactorial detrend fluctuation analysis. That get rid of the non-stationarity of the time series, and then we try to window the thing. Okay. So I don't know. According to you, should we look at the detrend fluctuation and then apply this method of extreme statistics to it?
Yeah, no, it could be actually. Because the point is that if you take off the trend, the only worry is that you might take off some of the important fluctuations, extreme fluctuations. Okay. So I don't know. By taking off the trend, of course, it's like a trend is more like the average value, right? So
Each is the train is like a drift term in the diffusion.
Yeah, drift term, exactly.
Yeah.
So I would say that, yes, no, if you take out the drift term, then that should be okay. Then you can actually use these stationary things. I mean.
Okay. So is there anyone actually write down a differential equation that's like diffusion equation or describing the change of this probability, joint probability distribution? The reason I ask is because when we look at the heart or the brain, right? For example, in the brain case, if you have a seizure,
right,
we think that there's a phase transition of the time series for given window size. So now our question, of course, this is all phenomenological, right? You look at the data, draw a conclusion. Is there a differential equation governing the phase transition?
This is a good question. I don't know. I have not seen anything. Usually, so I mean, estimating a joint distribution is always very hard. Okay, it's not always easy.
Yeah.
And so that's the point. I mean, so what people do is often, you take a simpler observable, like the density or some number or something, or mean value, and then it probably for some moments or something, or just 1 point density, probably you might be able to write a differential equation. That also depends on the model, but generic differential equation is very hard to calculate.
And what I think Bruce West and Paulo Grigolini has mentioned something about the differential equation may be a fractal differential equation because of the power law.
Fractional differential equation. Yes,
okay.
Right,
okay, good. And I'm going to ask another more kind of theoretical question.
Go ahead.
Yeah, you mentioned, I wonder, you talk about the gaps between eigenvalues, right?
Yes.
I wonder the trace rhythm distribution has to do with the distribution of the prime numbers gaps.
Well, not quite actually, because Tracy rhythm distribution, the way it appeared in number theory is actually, if you look at the famous Riemann zeta function zeros, right? So the Riemann zeta function zeros are on the imaginary half line, right? So So and then if you go high up in the on the imaginary axis, and then if you ask, I take some window and I look at the distribution of the largest root in that window, okay. And so that actually often behaves like Tracy rhythm distribution, because effectively, because you can, these zeros on this window, high enough window, you can map it to GUE essentially, okay, the Gaussian unitary ensemble of random matrix theory, and that's why you can see the Tracy rhythm distribution. But the prime number theorem, I do not see any Tracy rhythm distribution there. Not that I know.
Because I think Dyson long time ago mentioned that the distribution of the eigenvalue in the random matrix approach is a stretch Gaussian.
Yes,
it's a stretch Gaussian.
Yes, this is true. But probably, I don't know. I know that some mathematicians have looked at it, number theorists. John Keating and Montgomery and other people. But what is the precise connection to prime number theorem? At least I have not seen anything yet.
Okay. All right. Maybe I should ask one more question that stay in my mind for a long time.
Please, go ahead. Go ahead.
We have looked at something called the current. When you apply voltage to a certain semiconductor, the current appears to be going from a power law to a stretch exponential. Okay. So we think that the change from a power law to stretch exponential corresponds to a phase transition of the structure or the dynamic of transport in the oxide. Okay. So I also found that the reverse is can be described by what is called the Mitterker-Fraker function. That means from a exponential to a power law has an analytical expression. My question is, can one invert the times so that we get a power law to stretch exponential rather than from a exponential to a power law?
Yeah, so there are, of course, various different ways to generate stretched exponential distributions, and so the one example I know, when you go from power law to stretched exponential, is for example, in the avalanche statistics, in earthquakes and other things. But I don't think there is one single unique mechanism to go from power law to stretched exponential distribution.
Okay. Is there any analytical expression for it, or even approximate analytical expression for it?
For what?
From the power law to the stretched exponential.
Power law to the crossover function, you mean?
Yeah.
Power law
Yeah. Is there any analytical or approximate analytical expression?
There is probably, but right now I cannot remember. I mean, I can say,
okay.
I can think about it and send you if you want.
Okay, because that is very interesting that we observe it. Physically.
No, that's
never understand why. Yeah.
No, sure.
Yeah.
No, that's very interesting. No, absolutely. So there should be some analytical function which crosses over from power law at early times to stretched exponential at late times. So I'll have to think about this a little bit. I don't remember immediately.
I try to look at the Fox function, but it's too complicated.
No. Yeah. Fox function probably is not a good thing. No, Fox function is not a good thing. No, but I knew. I mean, right now it doesn't come to my mind, but I knew some examples of that. But I'll try to remember and then.
Okay, let me know. I'll appreciate that.
Unless your exponent is very small, in which case both behave the same way, right?
That's true. So that's why it's sometimes very hard to distinguish between stretched exponential and power law, of course.
Yes, small exponential. Gemunu, you had a question?
Yeah, first of all, very nice talk.
Thank you.
So my question is kind of a practical one. Let's think about when to find a bridge is going to collapse.
Okay.
So suppose you found out that the extreme values, extreme stresses in this problem follows one of your rules, maybe a Weibull distribution.
Okay.
The question is, does that tell you what kind of precursors to look for failure?
So this is a good question, of course. I mean, this. So basically, you are asking the stress in your material, and it's sort of response to the extreme, basically, right? So
right, yeah. And if you knew what kind the extreme distribution is, this is tell you what to look for.
Yeah, what to look for. No, this is a good question. I don't know if anybody has systematically studied this. I mean, I know this also know. I mean, probably. I mean, in the context of this, cracks and things like that.
Right.
I mean, at least by these old papers by Setna et al. And then Zapperi and company and all other people also, and so they were also looking at but I mean, I don't know whether they used really, the extremes to estimate the threshold of the stress. I mean, yeah, that's an interesting question. Yeah. So I don't know. Yeah.
There is a question from Shudong, who one of my colleagues here.
Hi, hello. Thank you for the nice talk. I just have a question on the entanglement entropy aspect from the perspective of extreme eigenvalues.
Yeah.
So imagine I have a system, I have a real quantum computer with, let's say, billions of qubits.
Mm-hmm.
So we'll be doing all sorts of manipulation on it and things like that.
Mm-hmm.
But from an overall perspective, would such a system be so different from a natural, strongly correlated system in terms of the extreme eigenvalue? Or
yeah, I don't know actually. Yeah, I don't know. This is a question. I mean, again, one has to, I think, rely on data to see. I mean, if really, if they, I mean, in principle, I mean, they can be cast again in this general setting of strongly correlated random variables, but precisely what is the nature of the correlations, I don't know. So that one needs to estimate from the data. I mean, this is the hard part, of course. I mean,
yeah, because in a large qubit array, you also only have, let's say, pair interactions and things like that, right?
I see. Yeah.
So you do these gates, but again, from overall scheme of things, they look like just local, some interaction.
I see.
And
so that would be interesting. That would be certainly interesting to this, because because this setting is very general actually, right? You can, I mean, take any set of random variables, you can put it in this general setting and ask for the extreme statistics now, and then you can ask what that would mean exactly in the context of your quantum computers, this I'm not sure, but that requires a thought. But yeah, but this is certainly an interesting place to apply, probably. I mean,
thank you.
One quick question I have, Satya, is for some years now we have been looking at what can be generically called rogue fluctuations. So these are basically very large fluctuations, and they come in very nonlinear systems. So strongly nonlinear systems, what happens is that the energy transaction primarily happens with localized excitations or solitary waves.
Right. Okay.
And when you have interacting solitary waves, they tend to break down and form smaller waves.
Right.
So if you let the system evolve, non-integrability essentially takes you to this quasi-equilibrium kind of a phase, which is infested with very large fluctuations.
Right. Right.
And this, when I say very large, it can be 6-7 times the standard deviation, right? And we have seen that in almost all the systems we have looked at so far, which is about 5 or 6 of them, the standard ones. Now, so the question becomes that whether one can actually make a prediction, because if one assumes that the ocean surface is also a strongly nonlinear system, then one of the things we cannot do is actually predict the rogue fluctuation equivalent of an ocean surface, which actually would be the rogue waves. And these can get up to like 110, 120 feet, pretty much, pretty quickly.
Right.
And ships are, by the way, built for only about 45 feet.
Right.
So what I was thinking about is, I can understand that the maximum probably can be, one can probably get an idea of the distribution of rogue fluctuations. And possibly one can think about what a maximum might be or guess it. Question is whether the extreme value statistics can give any insight by domaining the system into when such a thing might happen. Because clearly you wouldn't expect such a thing to happen in the early times. Early time, you have something breaking down. But there would be
but this is this is the sort of the question I was, I didn't have too much time to talk about it, but it's sort of related to the fact that people also look at the distribution of the Tmax, the time at which the maximum occurs. Okay. So if you look at it, there's a lot of studies on this Tmax. And so Tmax statistics often can, and there are really amazing surprises in the distribution of Tmax. I mean, so for instance, I mean, if I just ask you, just a Brownian motion, okay? Take a Brownian motion up to time t, and you ask, where does the maximum occur? I mean, at which time the maximum occurs? So you take a Brownian motion, random occur starting at the origin, you let it go up to n steps, and you ask, what is the probability that the largest displacement occurs at some intermediate time tau? Okay. Now, what would be your guess? I mean, like, typically, I mean, I would have guessed normally because it's a symmetric random walk, right? So you would say, the distribution of the Tmax should be a sort of bell-shaped curve, right? Something like this with a peak somewhere around t/2. Okay.
One would imagine so.
It turns out it's exactly opposite that. Okay. It's actually U-shaped curve. Okay. So your window size is, let's say, capital T. So you're looking at up to capital time T. And you ask, what's the probability that the Tmax occurs at little time t in between? So it turns out that it occurs either at very early or at the end of your observation period. Okay. So what that means that in Brownian motion, the typical trajectories, if you look at that, what does it mean? The maximum occurs right at the beginning. That means most of the trajectories has gone on the negative side, right? Yeah. And when it occurs at the other edge, that means, the maximum occurs at the very end. That means typically it's sort of on the positive side. Okay. So the Brownian motion is very atypical. It's not a typical stochastic process in that sense that, even though it's symmetric, but once it is on one side, it tends to stay on that side for a long time. So it's very stiff. Okay. So the distribution of Tmax is actually very important in many of these stochastic processes and, the time series and so on. And so I guess, I mean, what you're asking, this is precisely a very important observable also that, not just the value of the extreme, but the time at which it occurs. And what we are recently also studying is is the correlation between Tmax and Xmax. I mean, if, for example, if it happens early time, does it mean a large fluctuation, or does it happen at late times? And what are the correlations between the time at which the event occurs, the extreme event, and the value of the extreme event? And there seems to be non-trivial correlations between them. So
in this problem, there is an interesting side story, because if you wait long enough, there'll be an infinite amount of interactions between the various tiny solitary waves, which would mean that you'll actually reach equipartition.
That's true.
So there is an intermediate period where this occurs. And this intermediate period can actually be quite long. So in some cases, we have found...
it's a long... it's a quasi-stationary state, right? So
it just hangs in there and
exactly.
almost never goes.
Yes.
So okay, I'm going to look at your papers to see if I can...
I think I don't know if people have studied the distribution of Tmax in this models, but that would be actually quite interesting. I mean, a simple model, I don't know which one you have in mind, but the one I remember about the quasi-stationary state was a paper by Stefano Ruffo and company, right? I mean,
I see.
It was a very nice, because they have a nice, I remember the numerical data where they had this quiescent state for a very, very long time. And they had some estimate about this period of this quiescent and things like that. So Stefano Ruffo and I think Shamik Gupta was one of them, authors.
I'm going to look for that one.
And David Mukamel also. And that could be interesting. Because they had a very simple model. I don't remember the model very well, but it's something like a kicked rotor model or something, noisy kicked rotor model. I see. And they found that the trajectories in this simple model actually do have this precisely the solitary wave kind of, and the quasi-stationary state.
Oh, interesting. Yeah, we started originally with the Hertz problem, with the granular chain problem. And since then, we have looked at the Fermi-Pascal problem.
Yes.
And the beta problem, the quartic chain. Right. And we have also looked at not as deeply in a problem where you basically, it's a 1D problem where you can imagine that there are electrons sitting at fixed positions initially. So everybody repels everybody, and then it's bounded. So it's a highly sensitive problem.
Yes.
And here also you begin to see that at late times. But this problem is interesting because although it's non-integrable, it's nearly integrable, because the electrons can't collide, right? Sure. The solitary waves don't really cross.
No.
And the perturbation...
There's hardcore repulsion,
Yeah, the perturbation is kind of a minimal perturbation, but it's an incredibly rich problem where you have solitary waves that stick around for a long time, and then smaller guys that actually play another game.
I see.
So it's like almost like a phase separated
different scales, basically, right?
This has been such a surprise of a problem.
Yes.
And it's actually somewhat tied to the Calogero-Sutherland model, right? But it's more basic because it's a 1/r.
Right.
And it doesn't have the sinusoidal aspect that's built in there for symmetry.
I see. Well, that's interesting.
Yeah, I'll talk to you about this because I'll have to think about.
I know this is very interesting, of course. These solitary waves are always very intricate, actually. So, and as you said, there are these different scales at which different pictures go on, basically, so which is nice.
Yeah, and they interact totally differently than what we know, which is so surprising. By the way, any other questions? I took up some time, so. I think we have covered everything.
Okay.
So with that, let us thank Satya for a fantastic talk. Now you will certainly have a nice Memorial Day weekend, I'm sure. I know that Subbu is headed to New Jersey. He joined from the road pretty much. Nathaniel is headed to Florida. So he joined from Michigan and is going to head out soon. So a lot of people chimed in, and I'm very, very grateful for making, for you joining us to make this into a success. So thank you so much, and thank you, Satya.
Thank you very much. It was wonderful.
Thank you.
And have a great weekend.
Bye.
You as well. Thanks.
Thank you. Bye-bye.